Questions about anything from last time? About anything? Well, I was about to polish off a calculation of this integral around a circle of radius r, and it turns out if you integrate 1 over z minus a around that circle, and a is inside the circle, that's going to spit out 2 pi I. And that's going to be an important thing for us. So I take a branch cut of the principal. There's the branch cut for the principal branch of the log function of z minus a. It starts at a and goes left in a horizontal direction. And I take a point a that's below that, and a point a epsilon and b epsilon, and I'm going to slide them into that red line. So I'll let C sub r denote the whole circle, starting at, I should name this point here. Let's call it, I'll call it little a. So that as epsilon goes to 0, a sub epsilon I'm going to slide up to a, and b sub epsilon I'm going to slide down to a as epsilon goes to 0. And so I'll let C epsilon, or maybe I should call it CR super epsilon. That's going to start at A epsilon and go around counterclockwise and end at B epsilon. Anyway, the integral along the whole circle would be the limit as epsilon goes to 0 of the integral around CR sub epsilon. And that function, 1 over z minus a, is the derivative of something on that set. So that's the integral of d by dz of the principal log of z minus a by the chain rule. dz, and we've got a fundamental theorem of calculus for the integrals of the derivative of analytic functions, an open set. That would spit out log at b sub epsilon, that's going to be a limit as epsilon goes to 0, of log of b sub epsilon minus a minus log of a sub epsilon minus a. Oh, I got too many a's. I should call this, I need something weird for this thing. Oh, how about W? W is this point right here. Little a is my point inside the region. Okay, and that is the limit. This is going to be a very simple calculation. That's the limit as we do the sliding. The log of this thing is going to be the natural log of the modulus of b sub epsilon minus a plus I times the argument of b sub epsilon minus a. And of course we'd have the same thing minus, same thing except with a sub epsilons where the b sub epsilon was. And notice that the real part, they're tending to the same thing. So this thing tends to the natural log of w minus a. And this does too. So those cancel. What? That's going to happen here. The real part's going to cancel. And look at this one, as the b epsilon slides down to the red line there, that argument is approaching pi from the top. And when the a sub epsilon slides up, that argument is approaching minus pi, because that's where the branch cut has the jump. And that's exactly what causes this integral to have a limit that's not 0. So this one's going to tend to pi as epsilon goes to 0. And this one's going to tend to minus pi as epsilon goes to 0. And so the limit here is going to be equal to, the real parts cancel, and I'm going to get I times pi minus minus pi. And so sure enough, that's equal to 2 pi I. And that's what I claimed. So that famous integral is equal to fact. By the way, the same argument works for other curves than circles. Any curve you can draw and make that line poke out at a single point, you can do this trick with. Any closed simple curve. So this calculation makes sense in lots of geometries. But the big fact here today is the integral around the circle of radius r of 1 over z minus a dz is equal to 2 pi I when a is inside the circle of radius r. And, of course, it's equal to 0 when a is outside. That's just Cauchy's theorem. That's by Cauchy's theorem that we demonstrated last time using Green's formula. Okay, so that's sort of a preliminary calculation that we'll need to know. Oh, by the way, this shows that 1 over z minus a does not have an analytic antiderivative. So from the previous, we know that if it did have an analytic antiderivative on that set, then that integral would have to be 0. So a conclusion, 1 over z minus a does not have an analytic antiderivative on, for example, C, whole complex plane minus the point A. That has a hole. So it's not simply connected. So being simply connected and not having holes is an important consideration when you're trying to cook up antiderivatives. Let's see. Oops. Now I can show you the famous Cauchy integral formula, which is an exciting moment. It's going to lead to a whole bunch of conclusions real fast that are kind of deep and interesting. So last time I did the Cauchy theorem. This time I'm going to do the Cauchy integral formula. We'll get a lot of mileage out of the Cauchy integral formula when we do it on a disk, but it holds in more generality. Let's suppose f is analytic inside and on. Remember what that means from last time. Inside and on a simple closed curve gamma. So let's see, the picture is I'd have a simple closed curve gamma All my domains look like a potato for some reason. There's gamma. And f is analytic inside and on. That means there's a neighborhood around the curve, open set, where the function is analytic. And not only that, but it extends to be analytic through the inside of the curve. So f would be analytic on this shaded region. And if you don't want to think about the Jordan curve theorem, then you give yourself a curve that has the property, that it has an inside and an outside. Almost any curve you're going to draw is going to have that property, especially things like disks and squares and stuff like that. So my f is analytic on this shaded region. And here's my gamma, the green thing, going around. And this, the Cauchy integral formula is for, let's say, suppose f is analytic inside and on a simple closed curve, and a is inside gamma. So here's my a, some point inside gamma. Then the exciting thing is the value of f at a is 1 over 2 pi I integral around gamma of f of z over z minus a dz. Mind-blowing thing. The value at any point inside is completely determined by the values on that curve. That means you can't push analytic functions around. They're kind of rigid. And that'll have a lot of consequences. It'll kind of mean they're very much like polynomials in a lot of ways. Let's see. I'll give you my proof of this thing. Let me, rather than drawing this again, let me copy it. Okay. Okay, here's my demonstration. In this picture, I'm going to take a little tiny circle about this point A. I guess I might as well make it green. And I'm going to make it go clockwise. Okay, and the idea is I'm going to use the Cauchy theorem to split this thing into two pieces. One piece is going to go, let's say I'm going to cut it like this. I'll have a cut here and a cut here. I don't like that cut. How about this cut? All right, and I'm going to think about going around this way once. And I'm going to think, let's see, this thing is counterclockwise, so it goes like that. By the way, this gamma has to be counterclockwise. That's part of the assumption. So I should have added here, gamma is oriented to be counterclockwise. If it went the other way, of course, there'd be a minus sign in the formula. F of A would be minus that thing if it was clockwise. Okay, so look at, I'm going to have two curves here. These cuts are on the top half. I'm going to go around that way to make it counterclockwise. On the bottom half, to make it counterclockwise, I would have to go the other way. Okay, and I'll call this the top. I'll have two curves. Gamma sub top half is the top half, and gamma sub bottom is the bottom half. Okay, those are two curves, and I like to call, usually I call my C sub epsilons. So this is a little tiny circle of radius epsilon. And that circle right there, I like to call, well, let's see, if it were counterclockwise, I'd call it C sub epsilon, about A, that little circle. But since it's clockwise, I'm going to put a minus in front of it to emphasize that it's going clockwise. So that thing's clockwise. Not my usual orientation. Okay. And those two gamma sub top and gamma sub bottom are simple closed curves in this inside of in gamma. And so that means the Cauchy theorem would implies integral of f around gamma sub top is 0, and the integral around gamma sub bottom is equal to 0. Okay, when you add them up, the cuts cancel each other. So add these. Note that the cuts, the purple cuts, cancel each other. Leaving, let's see, so when the purple cuts cancel, that just leaves us the integral around gamma of f dz, that's the outer part, plus the integral along the inner circle oops, what am I doing? I'm sorry. I want to integrate the Cauchy integral. My thing inside the integral should be the Cauchy integral. I screwed up here, so let's see. Give myself some more space. I'll fix this easily. What I really wanted here is the Cauchy integral stuff. F of z over z minus a. F of z over z minus a. Because that's analytic inside and on, that simple closed curve, the top half. And that function, and also analytic inside and on the simple closed curve, the bottom half. So my Cauchy theorem says those are going to be equal to 0. And now when I add them up and cancel the purple cuts, it gives me that the integral around the outside plus the integral around the inner circle adds up to 0. And once again, I need to put this where it belongs. Here. And here. Oops. dz, dz. Okay. And this thing I'm going to show you, well, let's see, what is this? This is going to be minus the integral around c sub epsilon of a of f of z over z minus a dz. So when I put it on the other side of the equality sign, it'll be a plus that. And I'm going to show you that this, so the last step is going to be to show that the limit as epsilon goes to 0 of the integral around that little circle of radius a of f of z over z minus a dz is going to be 2 pi I. times f of a. And that's going to be an easy calculation. Let's see how it goes. Let's write integral, this thing right here. I'll copy it. This I'm going to write that 2 pi I, I'm going to write as the integral around c sub epsilon a of 1 over z minus a. So if I were to subtract that here, I'd get minus f of a, this is 2 pi, times 2 pi I. So that's where I'm going to put this, this thing, c sub epsilon a of 1 over z minus a dz. That's just 2 pi I. And you realize, oh, that f of a is a constant, so I can put it inside the integral. And so that this integral becomes, I've got the modulus of the integral around c sub epsilon of a. Let's see, on the top I'm going to have f of z minus f of a. This is going to look like a difference quotient. And of course, that thing goes to a limit. That goes to f prime of a. And we're integrating around a little tiny thing. So in fact, that has a maximum, and times the length of the curve, that's going to give me something that goes to 0. In fact, I don't actually need very much to show that this tends to 0. In fact, why don't I do it like this? This is less than or equal to the max of f of z minus f of a. I mean, okay, and z minus a on that little circle, that modulus is equal to epsilon for when z is in the circle. That's because the modulus of z minus a equals epsilon on the circle of radius epsilon about a. So that denominator, that looks bad. That's a 1 over epsilon kind of thing. But the length of gamma, the length of this circle, is 2 pi epsilon. And so, sure enough, this tends to, let's see, this is going to tend to, that epsilon's going to cancel, and I'll get that this is less than or equal to 2 pi times the max of f of z minus f of a when z is on that little tiny circle. And of course, that goes to 0 because f analytic implies f is continuous. So, in fact, all I need to know is that f is continuous. I didn't even need to know that difference quotient has a limit because f analytic implies f is continuous. So as that epsilon gets small, that max tends to 0. Questions about that? let's think about the case of a disk, which is kind of nice. Questions about that? There's lots of different ways of doing this. This is the way the book does it. Makes it kind of pop out quick and easy. Let's think about a disk. Okay, so I'll have my disk here. I'll have a center point, what do I call the center point? A. And I'll have a point Z in the disk, like that. Let's call this C sub R about A. So that's a circle of radius R. And I've got my Cauchy integral formula is that f of z is 1 over 2 pi I integral around the circle of radius r about a of, I'll have a w going around this circle. So this would be an f of w over w minus z dw. I want to differentiate this with respect to z to see if I get a formula for f prime of z. So the plan, differentiate the Cauchy integral formula with respect to z. Okay, the difference quotient is going to be f of z minus f of z naught. That z naught and z are going to be close together, of course, in that picture. When I write the difference quotient, 1 over 2 pi's would float along in both, and then I'd get an integral. F of w is that's going around, that's a parameter, so that would be here. But then the z's appear. 1 over z minus w would be the first one, and 1 over z naught minus w would be the second one. Okay. Oops. 1 over... Oops, I haven't divided by z minus z naught yet. I'll slide that z minus z naught in here. That's just a constant in the integral because the integrals are with respect to w. And the amazing thing is, you do the algebra. You cross multiply that mess. Let's see, what is this mess? Let's do it. The top would be, I'd have a z naught minus w minus z minus w over z minus w times z naught minus w. That's the numerator. Divided by z minus z naught. What am I doing? Yes. That was stupid. Sorry. That's going to make me look smarter here for a minute. W minus z. W minus z naught. And now, thankfully, what do I get when I do this? When I cross multiply, I'm going to get w minus z naught here minus w minus z here. The denominator is okay. And so the numerator in that thing is z minus z naught. And that's going to cancel the nasty thing in the denominator. So it's just junior high algebra shows that that difference quotient is nice and clean to look at. It's the integral around the circle of f of w times when you clean it up, the z minus z naughts cancel. That's the miracle. And we're left with, I got to fix the bottom here too. It's w minus z times w minus z naught. Now it's fixed. So that the z minus z naughts cancel, and I'm left with a nice clean w minus z times w minus z naught dw. So you stare at that for a second, and guess what happens as z tends to z naught? So we're going to guess as z tends to z naught, that's going to be w minus z naught squared in the denominator. So we guess that's going to go to 1 over 2 pi I integral around c sub r of a of f of w over w minus z naught squared dw. And you stare at that for a second and realize, oh, you know what I'm really doing here? That's what you get if you differentiate under the integral sign. That's what you expect. Of course, we don't know we can differentiate under the integral sign. This is showing you that soon we will. That's what you expect from differentiating under the integral sign in the z variable. The w variable is a dummy variable. So, actually, I have to show this. So, why it works. Okay, so if I take the difference quotient minus my guess, okay, let's see what was my difference quotient turned out to be. My difference quotient turned out to be 1 over 2 pi I integral around the circle of radius a f of w times, okay, the difference quotient turned out to be 1 over w minus z times w minus z naught. And my guess looked very similar. It's the same thing, but this one is w minus z naught squared dw. And I do that same algebra. So do this, it's very similar. I won't bore you to death with the algebra this time. But this time when you do the algebra, you get a z minus z naught in the numerator, and you get a w minus z times w minus z naught squared in the denominator. And so the great thing is, z minus z naught is a constant in that integral. I can slide it outside, and I get 1 over 2 pi times z minus z naught outside the integral times I took the modulus.
Oh, okay, yeah.
And then I got the modulus of the integral of something I can bound very easily. And so that's going to be less than or equal to 1 over 2 pi z minus z naught times the maximum modulus of f on the circle. That would be bounded because f is continuous there. And now let's think about the maximum of the rest of this stuff. That would be the maximum of 1 over w minus z times w minus z naught squared as z goes around, as w rather goes around that circle. Times the length of the circle, which would be 2 pi r. That'll cancel the 2 pi in front, but who cares? Okay, and here's how you would, I just have to show that this is bounded. So this is a less than or equal to some m, no problem. All I have to do is to bound this. By something. And then I would get that my limit goes to 0. So my guess was correct because of the z minus z naught. This goes to 0 as z tends to z naught. So my guess is correct. I can differentiate under the integral sign. I'm only going to do this once. Once you've seen it, then you're free to differentiate integrals. Okay, so the bounding that is a snap. And just draw a picture. Remember, I got my green circle here. Got my point. I've got a point z naught. I would draw a disk, draw a circle around my little circle here of some radius, though, so the picture looks like this. This is going to be a small disk. And my z is going to be in here. And if you look at, and my w, of course, is going around the outside. So once I draw that picture, I realize the z and the z naught are staying well away from the w. So if I make that epsilon small enough, so what's this distance here? Let's call this distance, it shows a bad spot for my w, kind of. My w is going around. Let's make this distance here be a d. Z minus w is bigger than or equal to that d. D would be going through the center here. That was a point A. So that's a radial line going out to the boundary. That's the distance between that little black circle and the little and the big circle. And so when you look at this denominator stuff, how small could those get? They can't get any smaller than d. So that top right thing, we see that w minus z times w minus z naught squared is greater than d cubed. As long as I keep my z in that little disk of radius epsilon. And so I get that max is less than or equal to 1 over d cubed. And so check. I can bound that. And the fact that I've got a z minus z naught in front is what makes that thing go to 0. Okay. what would the D be? Yeah, let's see. Yeah, I'll settle that picture proof. Any questions about that? So this leads to an exciting thing that's going to give me a whole bunch of really fantastic results, namely a higher order Cauchy theorem. Let's see, the higher order Cauchy theorem is that one derivative is 1 over 2 pi I, what you get by integrating around the inside. What am I saying? By differentiating under the integral sign with respect to A. And there's no reason why you shouldn't try to do that again. And in fact, exactly the same algebra is going to show that you can differentiate under the integral sign again. And this time you get 2. Let's see, what do you really get? When you differentiate with respect to A, you'd get 2 times that to the z minus a cubed, but it's a minus a in the bottom. So you get minus 2 times minus, which is a plus 2. So maybe to emphasize that this would be a minus 2 dz. So that's differentiating under the integral sign again with respect to A. And et cetera, you can keep doing it. And you can, let's say you do it n times. The nth derivative at A would be, when you do it n times, you get a plus n factorial up here. And here, on the last one, you'd get z minus a to the n plus first power. Those are going to be very useful. In fact, next time, I'm going to demonstrate the fundamental theorem of algebra using only these facts. And how exciting, I promised this fact. Let's see, the algebra of doing this again and again is all the same. So the showing this n times is very similar to doing it just once. Is same as doing it once. It's just that the algebra gets uglier. Just the algebra gets a little bit. You got higher powers to deal with, but those cross products do exactly the same thing. The z minus z naughts pop out in front. Just the algebra gets uglier to look at. It's the same algebra, it's just uglier. I'd call it bigger. You get more terms. But the main idea is the same. So it's the same concept exactly. Not hard to write it out, it's just I don't want it. It's the same and I'll bore you to death. But the mind-blowing thing is that promised fact pops right out. Promised big fact pops right out of this. Namely, F analytic implies that the derivative is complex differentiable. And there's the formula that gives you the derivative. And you can differentiate F prime, and so that implies that F double prime is analytic, etc. Dot, dot, dot. And so all those things I was telling you we're going to follow are now demonstrated. So consequently, if I were to write f of x plus iy is u of xy plus v of xy, I v of xy, we needed that fact to know that f analytic would imply that those things are harmonic and infinitely differentiable. And not only that, they're C infinity smooth. That big thing. Let's see. So the exciting moment here is that first formula where I differentiated once is going to lead to a very quick and easy proof of the fundamental theorem of algebra. Next time, this formula, f prime of a equals 1 over 2 pi I integral around a circle, and I'm going to take a circle of big radius about the origin of f of z over c minus a squared dz was going to imply two things real quick. Liouville's theorem, which is a famous one, and that's going to imply the fundamental theorem of algebra. Something people have been telling you since you were in junior high, but never showed you why it's true. So the fundamental theorem of algebra. And it's going to be quick and easy, not nearly as technical as today's work. So get that technical work behind you, and this pops right out. Let's see, I should tell you what Liouville's theorem is. It's very simple to state. A bounded entire function must be constant. Entire function must be constant. Okay, so bounded, entire function means analytic on C. And bounded means the function is bounded by something. So it's a very simple thing to state. That means that there's nothing like sine of t. Sine of t is a bounded function on the real line. So Liouville's theorem is way false. R to R. Sine of t is a bounded entire function. Is bounded by 1 on R and infinitely differentiable. In fact, it's given by a power series. And C infinity. Okay, there's no such thing in the complex setting. Being complex differentiable on the whole complex plane and bounded means you're constant. So we would consequently know that Liouville's would imply the complex version of the sine function can't be bounded.